Okay, in section 2.8, we're going to look at subspaces of Rn. So Rn, right, we know is the real numbers. You know, R2, for example, is the Cartesian plane that we're familiar with, XY coordinates, so forth. R3, three-dimensional, and that expands upward. So that's, you know, the general, usual representation of graphing in these spaces, okay? And so a subspace, then, is a subset of that, but it's a particular subset of that, okay? So a subspace of Rn is any set H in Rn such that we have the following three properties. Okay, property A, the zero vector is an element of H. Okay, that's the zero vector. Remember that E type symbol means is an element of. So this is zero vector set H. Okay. Condition 2, if U and V are in H, then their sum, U plus V, is in H. And then a third condition, if U is an element of H and C is a scalar, okay, so remember our U's and V's here are vectors. Okay, I know it's hard for me to emphasize the bold vector look there, but these are vectors. So U is in H, C is a real number, a scalar, then any CU, so scalar multiplication, is also in H. Okay, so those are our three conditions for a subspace. We have that the zero vector is in the subset, it's closed under addition, and it's closed under scalar multiplication. So closed under addition and scalar multiplication. Now, we can also think of conditions B and C together. We can think of that as CU plus DV is in H. Right? So we have the same ideas that we had before, where we can use those in concert if we're thinking about how to show it similarly. Okay, it's much like linear transformations. Remember, we had a similar idea for linear transformations, combining those two. Okay, now if you look at this notation, the CU plus DV, that looks a lot like a linear combination. So if I have a set of vectors U and V, then I have x1u plus x2v. This is a linear combination, okay? Maybe this is equal to something b, okay? Well, this is a linear combination of my vectors u and v. So linear combinations relate very closely to subspaces, okay? Now, notice if instead of putting b here, if I change this to a homogeneous equation, make that 0, well, then I would have to have the trivial solution. Okay? The trivial solution would have to be here. I could have non-trivial solutions in addition to this, but I would definitely have to have the trivial solution. Okay? So all of my solutions to this start out at the origin. Okay? Now, I could have another solution that maybe that's a vector w. Okay? And the vector w is equal to x1, x2. That solves this equation, this homogeneous equation. And then I would get all the multiples of it. And all the multiples of it form a line through the origin. So if I have a line through the origin, then I'm going to have a subspace, because if I take any multiples, if I add w to w, I still get another multiple. So all my multiples are on here. Any sums of this just gives me another multiple. The zero vector is included, okay? But if I look at a non-homogeneous system, like I had before, we know from chapter 1 that if I have a non-homogeneous solution, a non-homogeneous system, then the solutions are the same as the homogeneous system, just shifted. Okay, so those solutions then to x1u plus x2v equals b do not pass through the origin. Notice the origin is missing here. And so without it being in the origin, then for a non-homogeneous, I'm not guaranteed. In fact, I would rarely expect it to be a vector space. Not a vector space, a subspace. Sorry. Subspace. Okay. Also notice if I look at a line not on the origin, if I put pick a point that's on that line somewhere, well, I need the multiples of that line, of that vector, to be in the subspace. And here, this single point is in the subspace, but any multiple of it would not be in that possible subspace, okay? So non-homogeneous is not going to give you a subspace. Homogeneous will give you a subspace, okay? Now, we also have another terminology we've used in chapter 1. We have what's called the span, right? And we know the span is all linear combinations. So I've written a span here. I have a set of 3 vectors. Now let me also make a note here. If I have this set without the span, this is a set of 3 vectors. It has no other vectors in it but those 3. Now if I say this is the span of that, now I have the linear combinations. So remember, the span is all linear combinations. Okay. So how did we determine what the span was? Well, I went through and I said, okay, which ones of these are linearly independent? Okay, if they're all independent, then I get the whole thing is in the span. There's all linear combinations. So the span here is going to be x1u1 plus x2u2 plus x3u3 for any x, vector x, that's equal to x1, x2, x3. Okay, so any x will work there, right? Including in particular the 0 vector, right? 0, 0, 0. And if I pick any values for x1, x2, x3, any weights, when I add or subtract, I'm just going to get multiples of these vectors, u1, u2, and u3. So I'll get simply another linear combination. So spans are subspaces, okay, automatically. By the way a span is defined, it must be a subspace, okay? Because when I'm looking at a span, I'm saying that it could be anything over here on the right-hand side of that vector equation, okay? Now, we're going to talk about 2 special types of subspaces in particular. Okay, the first is called the column space. Okay, and the column space is the set of all linear combinations of the columns of a matrix. Set of all linear combinations of the columns of a matrix. That corresponds to the column space. Okay, now you're thinking that's a really similar definition to span, and the answer is yes. Span is all linear combinations of some vectors. The column space now is all linear combinations of columns of a matrix. Okay, and we usually write this with COL for column space of a matrix. Let's name that matrix A. Okay, so the column space of A then is abbreviated col A, or column A. Okay, and so the columns of a matrix can be thought of as vectors. If they're vectors, it's a span. If it's the columns of a matrix, then we talk about the column space. Okay, so they do mean very similar things, if not exactly the same thing. Okay. All right, so let's go take a look at a matrix A here and work some examples, talk about some definitions and ideas here. So 3, 2, 1 for the top row. Second row is going to be -9, -4, and 1. And the bottom row is going to be 9, 2, and -5. 9, 2, and -5. Okay, so I have my matrix A. I'm also going to give you a vector B. And that vector B is going to be -5, 7, and 1. Okay. Now the question is B in the column space of A? So in order for B to be a linear combination, so remember, column space is linear combination of the all linear combinations of the columns of our matrix. So if B is going to be in that, it needs to solve this system. Okay, ultimately I'm asking, is there a solution for AX equals B? Well, we have several ways that we've searched for AX equals B. Okay, our most common probably is the augmented matrix. So 3, 2, 1, -9, -4, 1, 9, 2, -5. Then I augment that with -5, 7, 1. Okay? And we're going to row reduce this, or just reduce it. Okay? Use your calculator. Use whatever tool is best for the job in your case. So go to your matrix on your calculator, 3 by 4. Okay? With my camera just a little bit here. So my top row is 3, 2, 1, -5. Second row, -9, -4, 1, and 7. Third row, 2, 9, 2, -5, and 1. Go back to our main screen. We're going to go to matrix, math. We're going to go down or up to get to RREF, or reduced row echelon form. Insert our matrix A. It's what we want to take the RREF, and we get this matrix here: 1, 0, -1, 1, 0, 1, 2, -4. Okay, so let's write down what that reduced echelon form is: 1, 0, -1, 1. Second row is 0, 1, 2, and -4. And then my third row, I should say, is all zeros. Remember, this is augmented. Okay, so this is a consistent system. So AX equals B is consistent. Okay, that means I could find a solution here. I could write that solution, right? X1 equals an appropriate thing. X2 equals an appropriate thing. We know how to write solution sets, hopefully from previous sections and chapters. So this is consistent. So the answer to the question is yes. Actually, let me write yes up here next to where the question is. Yes, B is in the column space of A because I have a consistent system. Okay? But as I look at the column space, or as I look at the columns of A, so don't worry about the augmented column right now. We know the row operations or the row reduction would be the same for each one. So notice here that if this were homogeneous, okay, so if I go to AX equals 0, I would write a solution set. I would get X1 is equal to X3, again, because remember we moved this negative X3 to the other side of the equal sign. X2 would be equal to -2 X3, and X3 would be a free variable. And I could write that solution as a vector as well, X3 times 1, -2, 1. Remember, because those are the coefficients there of X3. Okay? So this particular vector is very important because it means I can take this vector, put it in for X, and generate a 0, a non-trivial solution. Okay? So if I do my matrix A times this vector here, I get a non-trivial solution. Okay? So that means this third column here is not independent. Okay? Remember, all these definitions go together. Okay? For example, I know I'm not invertible because I have a free variable, X3. I know that the columns here do not span all of R3. The columns here only span a two-dimensional subspace. Okay, those first two columns. Okay, so when I'm looking at this, my column space really is only the two independent vectors. Okay, adding a third dependent vector does not give me any new information about my space. It doesn't add anything. Okay, so the column space of A can be thought of as the span of just the first two vectors, okay, just the first two columns, 3, -9, and 9, and then the second one then with 2, -4, and 2, okay? Column space of A is just the span of those two vectors. Now, it is also the span of the third vector. If I put the third vector here, 1, 1, -5, I still get the same space. But I'm not giving extra information. I'm making it harder on myself to deal with my space that I'm interested in by simply giving it additional criteria to reckon with when those criteria don't actually change what space I'm dealing with at all. Okay. All right, so that's the column space. Okay, the column space is all linear combinations. If we're looking for if a vector is in the column space, we simply take the augmented matrix and see if I have a consistent system. If it's inconsistent, it's not in the column space. If it's consistent, it's in the column space. Okay, so let's do one more talking about the column space. So continuing with the column space here, I'm going to have column A is equal to, or let me not say col A. We're just going to say A for now. So A is going to be -1, 1, 0, 2, 3, 1, 6, -2, 1, and 3, 1, -2. Okay, so notice A is not square, okay? I have 3 columns but 4 rows, okay? So the vectors in the column space of A, remember col A, so let's label these rows A1, A2, A3, these columns I should say. So we know that the column space of A is equal to the span of the 3 columns, A1, A2, and A3. Okay, we want to first determine if these are independent vectors or not. So get you a matrix. Okay, it's going to be a 4 by 3 matrix this time. -1, 1, 0, 2, 3, 1, 6, -2, 1, and then the fourth row is 3, 1, -2. Remember that a typical calculator will not do RREF of a 4 by 3. If you have more rows than columns, you have to make those match up. But you know you just stick a row of column of zeros on there and it will do the work. Okay, so A is a row equivalent to a matrix that looks a lot like an identity matrix, but is not an identity matrix, okay, because it's short, so to speak. Okay, it's missing that 4th column of the hypothetical identity matrix. Okay, but we know that I have a pivot in every row. I'm sorry, a pivot in every column is what I wanted to say. So I know the vectors are independent. Okay, so the column space of A is equal to the span of all 3 vectors. But notice that this column space is not equal to all of R4. Okay? If I take a similar matrix where I just chop off a piece here, so I take B, and B is just those first 3 rows. Okay? I know from the way that A row reduced that I'm going to get the identity here now in R3 because I don't have too many entries this time. And so the column space of B is in fact all of R3 because I have an invertible matrix. That means the vectors span the entire space, the entirety of R3. All right? So invertible matrix theorem tells me that that is going to be all of R3. Okay, now in my matrix A, while it was not all of R4, it is a subspace. Okay, we know it's a subspace because it has the 0 vector included. We always have the trivial solution. We know that linear combinations are there because it's span. And if I have linear combinations in the 0 vector, I know I am a subspace. So it's a subspace of R4. Okay, so the column space of A is of R4, is a part of R4, but it's not all of R4. Okay, now I said there were 2 special subspaces we were going to look at. The second is called the null space. Okay, the null space is the set of all solutions to the homogeneous equation AX equals 0. Okay, and we represent that then with NUL, null of A. I know it seems silly that they leave off just the second L as an abbreviation, but that is the standard abbreviation. It's just NUL for null space, like COL for column space. Okay, so the null space of A, or null A. Okay, and we know that that's going to be a subspace because if I take 2 vectors that are solutions, right? I have some solution. I know that if these are in the null space, U and V, right? So U and V are elements of the null space. Then AU plus AV is just equal to 0 plus 0 because I know these AU has to be 0 because it's a solution there. And so I get 0 there. Clearly the 0 vector is in this space, right? 0 is definitely an element of null A because it's the trivial solution. Okay? So clearly a subspace meets all those criteria without too much worry. Okay? So to figure out if a vector is in a null space, what we do is we simply multiply. Okay? So pick your your favorite matrix that you like, right? Let's say A is going to be equal to 1, negative 2, 1, 2, 0, 2. Negative 3, 1, 1. Okay, so as I look at that matrix, I want to do some row operations on it, maybe. But I want to know if B equal to negative 1, 2, 3, is B an element of the null space? Well, the easiest way to find out is to simply multiply. We know that if I do A times the vector, I should get 0 in order to be in the null space. So 1, negative 2, 1, 2, 0, 2, negative 3, 1, 1. And we're going to multiply that times my candidate vector here. And so I multiply. Negative 1 times 1 is negative 1. 2 times a negative 2 is negative 4. Put those together, I get negative 5. 3 times 1 is 3. So the first coordinate is negative 2. Well, I know that's not going to be the 0 vector. Even before I find the other two coordinates. It's clearly not the 0 vector. So if you multiply those and it's not the 0 vector, then you know that B, my vector here, is not an element of the null space. Okay? So is B an element of the null space? No. Okay? Now, since the null space is AX equals 0, right? It's all vectors that solve that equation. If I'm looking to understand what the null space is, well, all I'm really doing then is solving the homogeneous system. Okay? So go in, take a look at your matrix. 1, negative 2, 1, 2, 0, 2, negative 3, 1, and 1. We're going to row reduce that, and I get the identity when I row reduce that. So what that means is this, for this matrix, it has only the trivial solution. Okay? That means that the only vector in the null space is the 0 vector. There's no other vectors. It has only the trivial solution. Okay? It means that the column space is all of R3 because these were all independent. So the column space and the null space fit together in that way. Okay? Now, obviously, the null space is not going to be always the 0 vector. We have plenty of times when I have non-trivial solutions. Okay? So let's take a look at one in our next example. Okay, so my matrix A is going to be negative 3, 6, 0, 1, negative 7. I'm going to have 1, negative 2, 1, 3, negative 1 in the second row. The third row is going to be 2, negative 4, 0, 8, and negative 4 in row 3. Okay? So let's find out what is the null space of A. Okay, the null space of A is everywhere that AX equals 0. So let's go through and let's row reduce this. Okay? Use your calculator, use row operations. It's not too bad of row operations because there's only 3 rows. Okay, but I'm going to give you the secrets here. So first row 1, -2, 0, 0, and 2. Second row is going to be 0, 0, 1, 0, 0. Third row is going to be 0, 0, 0, 1, and -1. Okay. So as I look at this now, I have a solution set. X1 is equal to 2x2. Remember, it's going to the other side of the equal sign for ax equals 0. And -2x5. X2. X2 is a free variable. So x2 equals x2. X3, there's nothing else on that line, so x3 is just 0 all the time. Okay? X4 is equal to x5. Again, because that -1 goes to the other side of the equal sign, it'll be positive. And then x5 is a free variable. Okay? So I have a solution set here. I could write this as a vector equation as well, a vector expression, I should say. I get 2x2, 1x2, and then there's no more x2s after that. x5 is my other free variable. So in x5, I have -2x5, nobody in the second, nobody in the third, and then 1 and 1 in the fourth and fifth equations. Okay? So these are my null space vectors. Okay? So I'm going to call these U and V. So the null space of A is equal to the span of those solution set vectors, U and V. So in order to find an expression for the null space or an understanding of the null space, you solve the homogeneous equation, the homogeneous system. Your solution set vectors, notice these are linear combinations, right? It's linear combinations of these two vectors, show you which vectors are make up the null space. Okay, trivial solution still there, so it's still a subspace for sure. Okay, now if I look at this matrix A, I could also figure out the column space here. So I can take the column space, and I notice I have 3 independent vectors: the first spot, the third spot, and the fourth spot. Okay. So what you want then is you want the span of those pivot columns. Okay, so I'm going to give them a name. I'm going to have A1, A2, A3, A4, and A5. And the pivot columns were first, third, and fourth. So my column space is the span of A1, A3, and A4. Okay, so notice the column space and null space kind of fit together. Okay, they're the same ideas. Now it's important when you do the column space that you take the columns from the original matrix. Okay, so in this case, our column space would be the span. I'm going to write out the vectors here just to emphasize what I'm saying. Be the span of the first vector, -3, 1, 2. The second vector, 0, 1, 0. And the third vector, 1, 3, 8. Okay, that would be the span of those vectors would give you the column space. Now, if you put other vectors in here, okay, remember this says a set of 3 vectors. The span is infinitely many vectors. So if you put other vectors in here, you're not going to get any new information. Okay, you're not going to get any new points, any new vectors, any new planes, anything like that, because you've already covered everything. And since I have vectors in R3, this is actually equal to all of R3 in the span. I have 3 vectors in R3. Okay. Now I want you to notice something looking at my vectors. My column space vectors were in R3, but my null space vectors have 5 coordinates. They are in R5. Okay. Well, my null space is in R5. So notice that distinction. Okay. Look back at your original matrix A. I had 3 rows and 5 columns. So there's that 3 and 5 again. Okay. So the column space is contained in Rm, because you have an m by n matrix, and the null space is contained in Rn. So rows for the column space, columns, I know that feels backwards, right? It's the column space. So when I say rows and columns, right, I'm just talking about that m and n. Okay. So for this problem, it was R3 for the column space, R5 for the null space. Okay. Now, we're hinting at something that we need to define a term for. So another definition here, our last definition for this section, a basis for a subspace H of Rn is a linearly independent set in H that spans H. It's a linearly independent set in H that spans H. Okay, so if I look back at my last problem here for A, these three vectors are linearly independent. We know because that is how that's where those pivot columns were. You know, the pivot columns are linearly independent. So these three vectors are in H. They are linearly independent. They span R3 because they're three-dimensional and I have three of them. So they form a basis for the column space and for R3. Okay. Now, your most common basis for Rn is going to be the set that includes, let's start over on that line. Sorry about that. Your most common basis for Rn is going to be the span of the set that includes all of the identity vectors. Okay, so you've got 1 and all zeros. Then you go 1 for the second position with all zeros. And that continues all the way till you have zeros with 1 for the last spot. Okay, for R3, that would be 3 vectors. So a set like R3 has more than one basis possible. Okay, most commonly, if we're looking for the column space or the null space, we simply take our original vectors, our original columns, and use the appropriate pivot columns. That was column 1, 3, and 4 here to give us a basis. Okay, my null space basis is, again, these same vectors I just found. Okay, we know they're linearly independent because of the way they're found. And we know they span the column space or null space, again, because of the way they're found. Okay, whether or not they span the whole of Rn or Rm depends on how many we have. I only have 2 vectors here for the null space, but they're in R5, so that clearly is not all of R5. That's only a plane in R5. Remember, 2 vectors makes a plane. 1 vector makes a line, 2 vectors makes a plane, 3 vectors makes a hyperplane. Okay, so if I'm looking for the basis of a column space or a null space, okay, I'm doing the same type of operations. For a column space, I row reduce that matrix. I know that all the vectors in there, all the pivot columns form a basis then. Okay, and then for the null space, I do the same row reduction, and I know that the solution to the homogeneous system or the homogeneous equation forms a basis for the null space. But notice that they are in different places, right? In our last example, R3 had the column space, while R5 had the null space. Okay. So one more here. I'm going to have a set of vectors. 1, -3, 2, 3 for the first vector, U1. My second vector, U2, is going to be 4, -4, 5, and 7. And then my third vector, U3, is going to be 5, -3, 6, and 5. Okay? So let's ask some questions about this. First, can U1, U2, U3 be a basis for R4? So is the set U1, U2, U3 a basis for R4? Okay? Well, we might say, I know I need to be independent. Okay? Well, even if they're independent, there's only 3 of them, and I need at least 4 for R4. So this is a definite no just because there's only 3 vectors. I don't have enough vectors for that. Okay? Now, I can check for independence. Okay? I can answer some other questions about this system. And if I row reduce this, I find that I get ones along the main diagonal, all zeros for a bottom row. And we see that these columns are in fact independent, okay? So the span of these three vectors is a subspace. These three vectors form a basis for that subspace, not for R4, but for the subspace. So if I have H is equal to the span of U1, U2, and U3, U1, U2, and U3 are a basis because they're independent. So in order to find a basis, you simply take your set and throw out any of the ones that are dependent. Okay? Now, if I say this is my matrix A, then the column space of A is in fact equal to H because I have all independent vectors, so I'm good to go there. The null space of A, notice I have no free variables. If I have no free variables, then the null space is just the zero vector because I always have the trivial solution. Okay? Now, we've hinted at something. I'm going to write it down as a theorem here, something that we've said. So this is theorem 13 in chapter 2. Now, you don't have to remember these theorem numbers per se. I just like to give you references to where they are in the book. It says that the pivot columns of matrix A form a basis for the column space of A, or call A. Okay, so to find the column space, you simply row reduce your matrix, identify the pivot columns. Now notice it's the pivot columns of A, not the pivot columns of the reduced or the echelon form of A. So you use the echelon form to find the columns, but then you pick the columns out from the original matrix A. Okay? To find the null space, you reduce your matrix, you find the solutions to the homogeneous system. Okay? Okay, so that finishes up our discussion of 2.0. There is one more example. I looked down at my page here and I thought I had done them all, but there's one more. So when we're talking about a subspace, let's say I have a subspace represented here, and this or a possible subspace, I should say, is the entire plane. Well, the entire plane is clearly a subspace, no doubt, okay? I can always add vectors and stay in the space. You know, any two vectors in R2 is a space. Okay, I can take a visual here. My visual is just going to be this one line that goes through the origin. Well, I know if I'm on a line that any other thing on that line is a multiple of a unit vector, you know, something smaller on that line. I can just do multiples, give me the whole line. Remember that grid type setup we had in chapter 1? I'm going to stay on that grid, so this is also a subspace. Okay. Now you have to be careful because what if I only have the positive side of this line? Okay, well the zero vector is in my space H. If I add two vectors, I'm still going to be in my space H. But the problem comes with what if C is a negative number? Well, if C is a negative number, that's going to send me out the other side. Okay. So if I only have the positive spots, that is not a subspace because that is not going to satisfy that third condition for scalar multiplication. So you have to cover all the positives and negatives with the scalar in order to still wind up with a subspace. Okay, so make sure you're careful taking that into account when you are looking at some of the problems and homework and getting yourself ready for quizzes and tests. Okay. Remember to keep an eye on those checklists. Make sure you get all the assignments completed, quizzes, tests, checks for understanding. I'll try to get things graded back to you as just as quick as possible. Make sure you're staying on top of the homework. Okay. If you have any questions about material, about linear algebra, that's great. If you have questions just about how the course is set up, or if you need to know if you're completing everything, let me know that as well, and I'll be happy to assist you if you get that figured out. Help you out with those troubles. Okay, so again, let me know if I can help. And I will talk to you for section 2.9 in our next video. Section 2.9 talks about dimension and rank. Okay, talk to you then.